Hello everyone. In this video we will be talking about trigonometric substitution. So what is this useful for? So first let's look at an example of something you probably did in Calc 1. So if you look at the definite integral here from 0 to 3 of the square root of 9 minus x squared. Now you were probably told that at the time you didn't really have a good way to do this using the fundamental theorem of calculus because you didn't know the antiderivative. But you could also interpret definite integral as area, right? And we know that the square root of 9 minus x squared is the semicircle, the top half semicircle of radius 3. And here we're just going from 0 to 3. And so we can just do, this is going to be pi r squared for the area of the circle, but over 4 because it's just a quarter circle. And our r here is 3. And so we're just going to get 9 pi over 4. That's great. But like I said, it only worked because this was a definite integral and we could interpret it as area. So if I remove that, if I make this an indefinite integral, and we're dealing with the square root of 9 minus x squared dx, how do we do this? Well, it's not something that we just have the formula for, right? There isn't an obvious u substitution here because while we do have a clear inside function, its derivative would be negative 2x, and we don't have an x showing up anywhere. So substitution doesn't seem to work. And then our last option, our newest one, would be integration by parts. But again, there aren't really parts here, right? We're not really seeing a product. And so your only real option would be to take the whole thing here to be your u, and it turns out that's just not really going to work out. So what are we going to do? Well, it turns out trig is here to save the day. So let's consider a triangle where sine of theta here is going to be x over 3. And we'll explain why this choice comes about here in a bit. For now, let's just see how it works, and then we'll talk about how to come to this from the start. So if we have x and 3 as our opposite and the hypotenuse, then the Pythagorean theorem is going to tell you that this third side is the square root of 9 minus x squared. So if I want to deal with the square root of 9 minus x squared dx, then I'm going to do a different sort of substitution. So if sine of theta is x over 3, well, what is x going to be? X is 3 sine theta, and therefore dx is going to be 3 cosine theta d theta, right? So now let's go ahead and substitute that in and see what happens. And suddenly this is going to look familiar to you who have taken kind of the first assessment and seen some weird looking trig identities. It was preparation for problems like this. So we're going to get 9 minus 3 sine theta squared, which is 9 sine squared theta. And then dx on the outside is 3 cosine of theta d theta. All right. So to simplify this, well, note that we have a 9 here, a 9 here. That can be pulled out as the square root of 9, or 3. Then inside we're left with 1 minus sine squared theta. And again, outside we have 3 cosine theta d theta. So now we would like to get it all in maybe one term. So what can we do here? Well, this is just cosine squared theta on the inside, right? 1 minus sine squared theta via the Pythagorean identity. So we have 3 times the square root of cosine squared theta times 3 cosine theta. Well, the square root of cosine squared theta is cosine theta, and so this turns into 9 cosine squared theta d theta. All right, well now we are most of the way done, because now this is something we learned how to do previously, right? We know how to deal with even powers of cosine. So we can pull out the 9, and our cosine squared theta we can rewrite using our trig identity as 1 plus cosine of 2 theta, right, our double angle formula here, over 2 d theta. And so when you do this out, since we've already done this one, I'm going to do it somewhat quickly, right? So we have the 1/2, that would be 1/2 theta times 9/9 theta. This guy becomes 9/4 sine of 2 theta, right? Because we'd have the 1/2 coming from the inside because we'll be multiplying by 2 plus c. Okay, so up here, I'm just going to remind us that we have x is 3 sine theta. So first, we need to get things back in x, right? We started with things in x. We want our final answer to be in x as well. So what is theta? Well, to solve for theta, right, we have x over 3 is sine theta, and thus theta is arc sine of x over 3. So here we have 9/2 arc sine of x over 3. Great. But then the problem arises here, because we can deal with sine of arc sine, right? But sine of 2 arc sine is a problem, right? That 2 makes things a little bit challenging there. We're not able to just use the properties of inverse functions and cancel things out there. So what we want to do is use a half angle formula to get rid of that 2 and get down to just theta. So let's also recall that sine of 2 theta is 2 sine theta cosine theta, right, from our half angle formula. And so using that here, we have 9/4 times 2 sine theta cosine theta plus c. Okay, so again, what did our triangle look like? This was square root of 9 minus x squared, x and 3. Why does this matter? Because we still need cosine, right? We know what sine is. Sine is x over 3, but cosine we need to be able to solve for as well. And so this becomes 9/2 arc sine of x over 3. This is also a 9/2. Sine of theta is x over 3. And cosine theta is the square root of 9 minus x squared over 3. Plus c, these guys would cancel with the 9. And our final answer, at long last, is 9/2 arc sine of x over 3 plus x root 9 minus x squared over 2 plus c. So you may now have the question of what substitution should I use, right? Like, how did I come up with this sine theta triangle? So if you see things of the form square root of a squared minus x squared, right, which is what we just saw, square root of 9 minus x squared, 9 is a perfect square, then you can always draw the triangle that looks like this, right? And basically, this will show up as one of the sides of this triangle. And so the other substitutions basically come from the other ways you can draw this triangle, right? So what is another option? Well, you could do one where you have tangent is going to be x over a, right? In which case, what is this side going to be? Well, you'd have x squared plus a squared. Okay, and so right up here for this one, we just use that sine of theta is equal to x over a, or that x is a sine theta. Here, we would use that tangent theta is x over a, right? In this case, just like theta was arc sine in the first one, theta would be dealing with arc tan in the second one. And then our final one here is going to be a down here, x here, and then your third side would be the square root of a squared minus x squared. And then in this case, we frame it as secant theta is going to be, right, this would be hypotenuse over adjacent, and so it's x over a here. Right, so these are basically all the ways that you can do x over a, and tells you basically exactly the substitutions you would need for these three cases. Okay, so these are the main three that will show up. Let's do one more quick example. Okay, so now let's look at, say, dx over x squared times the square root of x squared plus 1. So again, this is something that we couldn't really do any other way. By parts and substitution just don't really work. But our hint to use trig substitution is this guy, right? And so which one should this be? Well, the square root of x squared plus 1 is the one that occurs on the hypotenuse. And so we should have x and 1 here. And so in this case, right, we could just use tangent theta is x, in which case our dx is going to be secant squared theta, d theta. And so when we substitute in, so our dx up top is secant squared theta d theta all over. So x squared is going to be tangent squared theta. And then the square root of x squared plus 1 is the square root of tangent squared theta plus 1. Now, if you are good about your trig identities here, this one uses the Pythagorean identity, right? So tangent squared plus 1 is equal to secant squared. So simplifying, this is going to be secant squared theta d theta all over tangent squared theta times square root of secant squared, which is just secant, right? So 1 power of secant goes away. And now all we have to do is figure out how to finish this off. So when looking at this, I don't immediately see how to deal with it. And so when in doubt, right, so like remember when you had to deal with the antiderivative of tangent, you just broke it down into sines and cosines and you saw that it was a substitution. So let's try something similar here. So secant is 1 over cosine, and then tangent squared is on the bottom, so this is cotangent squared. So we've got cosine squared theta up top and sine squared theta on the bottom, d theta. So cosine cancels. And now we have sine squared theta in the bottom. So this is just cosine theta up top, or cosine theta, times sine to the minus 2 theta d theta. Well, now this just looks like a u sub, right? So u is sine theta. We see it to the negative 2 power. du is cosine theta d theta. And so to finish this off, this becomes just the integral of u to the minus 2 du, which is negative 1 over u. So that's negative 1 over sine theta. And then we have a plus c. And so for your first exercise, so exercise 1 here, I want you to rewrite this in terms of x. Right, so we've got it down to negative 1 over sine theta plus c, but we don't want a theta there, we want x. So I want you to rewrite that in terms of x. All right, and for your second exercise, I want you to go ahead and compute the integral of the square root of x squared plus 1 using trig substitution. Thank you for watching.